And that's the key. So welcome everybody. This is your teaching staff. We're doing the special guest office hours for fall 2019. Wow, can you believe it, 2019? But today we have James. Well, I should probably attempt the full name. So Dr. James MacGlashan.
That's right. That's good.
Oh, okay. That's lucky me. He is a senior senior research scientist at Kojitai. And if you haven't researched the company, I highly recommend you do because it has a pretty nice crew in there. He received his PhD in computer science from the University of Maryland. And then he did a postdoc at Brown University with our professor, Littman. One of the things that I really get excited about James is that he's written so many different reinforcement learning algorithms that you cannot even imagine. In fact, before OpenAI Gym existed, he had a library that basically did the same thing in terms of environment. So there's a lot of environments in Burlap, is the library that I'm talking about. But there are also algorithms, so implementations of the solutions of many algorithms, not just reinforcement learning, core reinforcement learning, but also dynamic programming like value iteration, pulse iteration. I think I even saw A-star at one point. I don't know if you still have it.
Yeah, A-star was in there too. Yeah, it's a classic, so you got to have it, right?
I know. And then so that's one of the best things, because I always say, like after you get hands-on and implement one of these algorithms, you learn so much. But if you implement a library that has environments and also algorithms, then you're the man. So I'm really happy to have James with us. I think, James, you also were an instructor at one point. Is that correct? Or a professor?
Yeah. So yeah, kind of. So actually, I did, when I was a grad student, I did some instructing. I instructed a few courses, mostly introductory courses back then. At Brown, I didn't do any instructing, but I transitioned to like adjunct professor status for a little while because, I'd been there for a few years, and so that's a good way to, give you a bump for a little bit. But I didn't do any formal instructing. I worked with a lot of students at Brown though, had a lot of fun doing that.
So yeah, that tells you a lot. So he has the theoretical background. He knows a lot of the theory of reinforcement learning. He has the practical background as well. He's implemented, unfortunately, Java, but I suppose that you do some Python too. But other than that, implemented so many different algorithms, and but also. He has presence in Quora. And I actually remember a few years back when I was trying to, also get some, answer some questions of myself. I saw these James guys being like top 3, and I'm like, I need to get this guy over here. So, no, yeah, but that, and he's also very helpful on Twitter. So if you have a question, reinforcement learning, or, AI, he really likes the conversation. And with that lengthy introduction, and I promise I'm not going to talk that much, welcome, James, to our class.
Thank you very much. Glad to be here.
Yeah. All right. Excellent. So the way we're going to do it is that Chris is going to be asking the student questions that you guys submitted a few weeks ago. Well, students submitted the questions, and then they voted for the questions they wanted to be here. So we're just going to go down a list of questions, and we're going to get some insights.
All right.
Let's do it.
All right. So the first question here. There exist several RL algorithms that can successfully solve different kinds of environments. Can you tell us in practice, how do you go about solving a new problem with RL? How do you choose your algorithm? Do you have a preferred algorithm you start with? DQN, A3C, PPO, soft actor critic? And can you tell us about your workflow?
Yeah, it's a good question because I think RL is still a lot of art right now. And so someone coming new into it, it's harder than like deep supervised learning, which has started to kind of have a nice, methodology that everyone can get into. But RL is still a bit of art that just takes experience. So the first thing I usually do is I do just ask myself, what do I know about this specific problem? So it's it's a lot of the different algorithms assume different constraints, or they assume certain kinds of things. So, for example, that the DQN and double DQN and all the variants people have done from there, generally they are going to require you to have a discrete action space that you're working with. And when you do, sometimes they work pretty well. But if that's not the case, it kind of throws them out almost immediately. There are some people that have worked in algorithms that are kind of like that, and they do something a little different. They usually do things like, oh, well, maybe we can do DQN, but when we have to apply that max operator, which is the real reason DQN, all those algorithms only work on discrete action spaces, they want to do a max over all the different Q values for all your actions. If you can't do that because there's like infinite, there's like continuous, or just really huge, people might do things like, well, we'll kind of pseudo-optimize it. So we'll run another optimizer in the loop to try and find the max there instead, or we'll do gradient descent on the action to try and find it and maximize it. And those approaches have had some successes, but typically that's if it's not discrete actions, usually actor-critic-like approaches are better. So that's like one example of that. Other things though that I also try and bear in mind is like sources of information. So one of the reasons I actually often like actor-critic algorithms is because if you can bring in things like you have demonstrations or you have a baseline control policy or something like that, actor-critic algorithms are great because there's a better pathway for training a direct policy object from those sources of information. So if you know, it's like, oh, actually, I'm starting this, I know there's some good information I want to exploit, then actor-critic algorithms can be really good for that kind of thing. So that's pretty useful. Sometimes you can do clever things too. If you know the reward function, sometimes you can make your algorithm a little bit more clever because you can encode that into it. So there's things like that you can exploit. Let's see, is there anything else I have in mind about just questions? Oh, I guess you can also kind of think about, are rewards sparse or dense? That might start influencing how you go down the pipe of what you're going to use for that. So I start there, and then you at least weed out algorithms that just can't work, right? So as I said, discrete actions is a non-starter. Oh, another big one actually that I think is super relevant is can you actually use parallel agents? Oftentimes when people say, oh, we're doing a simulation, they just assume, well, we get parallel agents for free. A lot of real-world problems, that's not necessarily the case. You're not going to get parallel agents. You have to do learning on the system. Other times you might be really data sparse, and so all those start pointing you towards off-policy algorithms where you can get a bunch of data and improve just on that data set. So that's kind of like batch RL-like algorithms. And those, of course, can also work with actor-critic methods. So you mentioned, like in that list, soft actor-critic is like an example of an off-policy actor-critic algorithm where you can just kind of take data and run on stuff like that. So those are probably the big questions I start with. If I am in a place where I know there's a baseline policy or there's demonstrations of how to do things well, a way that I like to kind of bootstrap the hyperparameter search process is you can do behavior cloning like algorithms on a direct policy object. And that just, because that's more of a supervised kind of thing, it lets you search the space of network architectures a lot more quickly. So that's a good way to get started. It can also give you, bootstrap some of the experiences you have that you can learn off of. Like I think actually, was it today they just, like DeepMind just announced their StarCraft 2 results, right? And that they have like a whole slew of approaches they're using that, but they like start with like imitation learning, doing like behavior cloning on a bunch of players already to seed that base. So that's a really good way to bootstrap things from a lot of angles. Other things you can do is if you don't have baseline policies, and you're doing off-policy learning in particular, this can be useful. Another thing you can do is you can try and just learn the reward function, right? Because that's another way to kind of ground out whether you have a good architecture that can learn from the data you have to predict the rewards accurately. If you're using something like like off-policy value function learning methods like DQN or the critic in soft actor critic, if you're using those, being able to learn the reward function is a very good proxy, because if you can't, those algorithms are going to have a really hard time learning the Q values if they can't bootstrap themselves from just learning the reward function accurately. So that's another thing you can do to try and do some search and try and see if you can get things working quickly from the start. And then it is just kind of a try things out, try and get a sense of. I don't know quite how to formalize this, but I often try and get a good intuitive sense of what your agent is experiencing. So if you think about what your observations are, try and internalize in your head what it would feel like if you had those observations. Sometimes you might realize that the observation space you have is more limited than you were realizing. So you'd be thinking about things in terms of, oh, well, of course I have this information, you should be able to do that. And then it's like, oh, but that piece of information actually isn't available. Why should I expect the agent to be able to figure it out? And you kind of start seeing what it'd be like to be blind to that information, and that can lead you down good paths from there. So those are I think all a bunch of things I would look out for. Other stuff is you do want to be a little careful about if you're using bootstrapping methods that you aren't like having your system diverge because you're refreshing your target network too quickly or something like that. A lot of these algorithms they're kind of all based in this fitted Q iteration kind of style of algorithms. We don't really have good theoretical guarantees that they'll work. And in practice, what the whole DQN Nature paper with Atari kind of shows, like, but we can, make it work. We can, if we're careful, we can make these things work well. But you don't get that for free, right? So you do have to make sure you're designing things and setting things up that your value functions don't start exploding from there. I think that's at least a good gist of some of the things I would start doing.
Yeah, the second question is kind of a follow-up on that.
Right.
So you mentioned that maybe learning the reward function is something you might look at. But given that these algorithms take so long to train potentially, are there any statistics that you're monitoring during training? Yeah,
there are some, right. I think often a really good one is looking at either your critic or just your Q function and tracking that against what your empirical rewards are. So even in actor critic methods, if it's off policy actor critic, like soft actor critic, then of course, if your value function isn't tracking your actual empirical rewards, you should not expect your actor to behave well at all, right? Because it's getting totally bogus information. If you think about it, if you just gave it the ground truth Q functions, actor critic kind of makes sense because then it's basically a supervised learning problem for the actor, right? It's like just maximize this function, go. That's straightforward, but it all depends on that being right. If you're using more of an on-policy algorithm that incorporates returns, so PPO, of course, is very much in that style. Anything that uses like advantage actor critic, they're using a lot of the returns to help things out. They're less demanding of this. In fact, if you go back to the original like reinforced paper and policy gradient theorem, you kind of don't need a critic at all. You just need returns in principle, and it works. Except it's really, really high variance if you don't have any kind of critic involved, and so things aren't going to learn very well. So it's still usually useful to look at whether your critic is estimating the empirical returns in a reasonable way to get a sense of whether you should expect it to start doing well. If that's not even learning well, the policy is not going to follow from it.
I do have a couple follow-ups, James. So, you work full-time, basically doing reinforcement learning. Now, I don't know if, it's probably just a single product, right? Not, multiple different, problems and solutions. However, how much of your time in the real world, right? So you got a job, one of our students gets a job, as a sort of machine learning engineer, right? Not necessarily a researcher because we're master's level in this course. But, how much of the work is actually tweaking the agent versus tweaking the environment?
That's a good question. It varies. It can vary a lot, right? Because it depends a little bit on whether this problem just is, right? This problem is handed down to you. You have to solve this problem and you can't do a lot, or if you can get in there and change things. So sometimes problem is what it is. You're not going to get a whole lot more from that. If you're doing things like on robotics, right? You can actually change a lot there. you can put on new sensors. You can put on new kind of sub-level features that are calculated. You can potentially change the hardware, to some extent. So you can iterate there, and that is a good way to go about it. To the extent that you can make your environment easier, you absolutely should. Like, you should always solve the most specific version of your problem, right? If that's actually the problem you care about, you should always solve the most specific version. Don't go more general than you need to. Exploit everything you got to do it. So sometimes you can get away with that. If you're doing things like something in video games where you actually are trying to deploy something with a game, you could, of course, change things there. Other times you have a little less sway. So at Cogitai, we do have a healthy mix of these situations where we get clients who are interested in some problems where some of them are doing like robotics-like things, and so they might have a fair bit of control of what they're doing. Others have like these embedded, so this is a fairly common thing we see of like embedded controller type problems, where normally they might have some kind of control theory-like way of doing things. They often don't have a whole lot of flexibility for what they can do. It's like the sensors they get are what they get, and you kind of have to deal with it. You can certainly still work in the feature engineering space, though. So that's something you always have some flexibility on, as long as you're not blowing up compute to crazy limits. So yeah, I think it just depends on what problem you're really trying to solve. Some problems you can and you should make it easier for the agent. Others, that's just what the problem you're trying to solve is, and you can't do anything about it.
Cool, thanks.
So this next question is more in the job market vein. So in traditional software engineering, there are many different roles based on skills and multiple levels of career path. Is RL still predominantly done in research and academia, or are there positions for people of multiple skill levels?
Yeah, so I would add one point of clarity to that, which is certainly industry is deeply involved in RL, but it's kind of in the academic vein, right? So DeepMind is industry, but they're basically publishing in academia conferences and things like that. So they're kind of, for all intents and purposes, academia. So I guess my answer would be, though, if you're applying RL, I think it is right now still mostly people who got a PhD or a master's working on that topic. They're usually the ones who are trying to apply it. For kind of reasons I mentioned earlier, which is RL is still kind of an art. It hasn't quite gotten to the point where you can just, throw methodology at things the way supervised learning has now become. And so because of that, it does need people who have a bit more expertise in it. That said, though, there's still lots of other ancillary things that go on with trying to do this. So, at Cogitai, we built a cloud platform so different clients can hook up things to our cloud platform, and it does RL. And right now, we often work with clients to help them figure out how they want to go about framing their problem and getting it hooked up, what algorithms they should choose, because there's a bunch of different algorithms you can choose. And as the first question, was about, which algorithm do you choose? There is actually some thought you have to put into doing that. So we do still work with people there, but there's so much other stuff that you can do that people can work on in this space that becomes important. So actually, we often have felt at Cogitai that we need to get more engineers. The core software engineers that we have are very good, but we feel like we have too few of them oftentimes. It'd be nice to have more. So some of that is just the like cloud and compute infrastructure, particularly for reinforcement learning things, can be really tricky to manage. It's more tricky than supervised learning, because supervised learning, you typically say, this is the data set, maybe, in a few months we'll refresh it or something and redo things, but you kind of have a nice static data set and you can, manage the memory a bit easier. In reinforcement learning, sure, to an extent, we often have found people are going to be in a more batch-like mode, where they're going to get some data and you want to do some things, and you'll get some more data and you'll do some things, but you still have to be able to process new data as you go. The agent, you're still usually going to have some agent in the loop that's going to collect data, do things, and you want to use that to improve on stuff. So that just adds a whole lot of software engineering challenges for trying to make these systems that work well. On other extremes for even like specific projects, I don't know like what the setup is at like OpenAI, for example, but their Dota, OpenAI 5, I guess, for Dota, that was a very serious compute setup that they had. And so there's just tons of just core software engineering related to it that has to go on to get that to work well. And I'll also say usually it does help also for these software engineers to know something about reinforcement learning because it has different kinds of demands. And so if you understand the demands of what it takes to do reinforcement learning, that's going to make you way better at doing the software engineering necessary to make it work. So there's a lot of stuff there. There's a lot of front-end stuff you can also do. So visualizations, often are game-changing for how quickly you can iterate on solving a problem. I don't know about other researchers, but my visualizations usually suck. I have a lot of visualizations, when I made burlap that were super useful, but they're like, here's a red square, and I know what that means somewhere. It wasn't super fancy, but you could do more with better visualizations. You have more complex things. You can get more insight. I think one of my favorite graphics from one of DeepMind's work is, I forget which paper it was, but it's when they were doing like the maze-like environment that they have, and they had this little GIF of here's what the agent's doing, and it's like here's like 15 plots, on the side. They're like showing the different activation functions of the networks as the agents walk into the world, the value predictions as it's going. I'm like, that is a really good visualization tool set. I can imagine that that kind of stuff helps a lot working on this problem. So there's a lot of ancillary stuff, even if you're not doing the absolute core application of trying to make these algorithms work. There's a ton of other software engineering related to this, and I can absolutely say software engineers who say they have experience with reinforcement learning is like a big plus in our book. So if you're interested in software engineering and reinforcement learning, I think there's a lot of potential there.
I have a kind of a follow-up. You mentioned good visualizations are kind of game changers in RL context. What comprises like a good visualization? Are there like metrics or charts that you find especially helpful when you're building out these algorithms? Yeah,
I personally find it very useful to inspect value functions a lot. I think they give you a lot of information. The policy network itself can be useful. I haven't done a lot of this specifically, but I always thought it would be nice to have some more introspection on just the image features that a policy might be looking at. In the same way we do in supervised learning, having more introspection on what the policy's thinking is relevant is probably super useful for figuring out why it starts doing crazy things, right? If you have an agent that sometimes it's like it does something like that seems totally bizarre, why would it do that? Seeing how it's looking at the feature space can be really interesting. I'm not sure if anyone did it, but like I can imagine in Montezuma's Revenge, right, which is a very hard task for reinforcement learning algorithms to solve. There's little things that are really hard, like you can pick up a key and then you get like a little key icon in the top corner of the screen. Like, so we know, as people having played these games, that little indicator on the top of the screen is like, switch your state context. Like a whole lot has changed. But if your algorithms aren't kind of focusing on that, that's going to be a serious problem. So I think when you get into image-based stuff, things like that can be really useful. But I think I do think value functions, just trying to introspect them as most you can be useful. There are, I can't say a lot right now about this, but I am kind of investigating some other ways to kind of get metrics and verifications that things are working, precisely because RL, as it propagates rewards back through things, it can take a really long time. And it doesn't mean things aren't working, it just means it's taking a really long time. And having a sense of whether that's actually working in a correct way, is super valuable. So there's not a lot of stuff out there for doing that, but that is something I'm interested in, and some other people at Coach Tai are interested in that we're looking at. And it might also imply some additional algorithm changes. So I think the space is really important because, yeah, RL can take a long time even if it's working right.
A follow-up on that follow-up. So you talked about image features. Are you talking about visualizing sort of like the network filters, or more like a saliency, style explainable AI? What exactly? Can you give us a little bit more insight?
Yeah, I think so. I haven't done a whole lot of this kind of introspection on images. More so, I've wanted it, but mostly I'm thinking about saliency type features in terms of what's paying attention to. I think something you could potentially do that'd be nice is looking at how, if you get to the value function, how does certain features change the value function prediction? Like you see something that's just kind of a smooth change in the value function when it should be sharp. That's going to be really important. So I'd have to think about it a bit more about how to really dive in to get that kind of information. But that's the kind of wants that I have, these kinds of image-based analyses that don't really exist super well right now, but would be nice if they did.
I totally agree about the value functions, by the way. If you think back to the Alphago paper, the killer chart there is like that Go board with like the value function visualized on the Go board, right? And it
right.
What the computer's thinking.
Yeah. I think it's also interesting to think about, like the Q function too. Some domains it's really hard to visualize how is it changing with actions. Go is at least it's a little more straightforward because it's like you put a piece here, like this, very 2D image like action space. Other things like robotics, you have like a bunch of joints that the robot can control, that it can turn, whatnot. Thinking about how to visualize that is hard, I think. But when you can figure out ways to do that, it gives you tons of insight. I feel like usually when I'm trying to figure out what's going on, once I start getting insight on what the value function's doing, that usually is the turning point.
All right, so this next question, having just mentioned AlphaGo, so with the recent success of algorithms like AlphaGo and AlphaStar and OpenAI 5, do you think this is causing a concentration in the study and application of deep RL to the detriment of other methods?
Yeah, so I think my answer is mostly no. I'm sure everyone has opinions on what the community is doing wrong, so I don't want to come out too hard. But for me, I think it's not so much deep RL's fault so much as it's just the direction people are going to perform RL research, which is everyone is very focused on simulators right now, like simulated games of things and how to do RL on that. So these really impressive StarCraft 2 results that just came out, it's a huge amount of training that goes on across many agents to fuel these things. Same with the OpenAI 5, even Atari to a certain extent, although much lesser so than some of these bigger projects that have been going on lately. Everyone's so focused on, well, can we just get it to work at all, that you get these huge amounts of compute that's often, I feel like, start to exploit things that were not meant to be exploited by the definition of RL. So I often have a pet peeve to make a distinction between reinforcement learning and planning. Reinforcement learning, as it's classically defined, what makes it not planning is you don't know how the world works. You have no model of how the world works up front. You have to just interact with the environment, not knowing that, and figure it out. And if you make a bad decision along the way, too bad. Like that's life. You're going to have to deal with it now, and that's what makes it so hard. And planning, I think, is actually a super interesting and useful area. That's why I have the word planning in burlap when I made it. It is an interesting place, but people have started to conflate RL and planning as being the same thing when they're not. And so sometimes people focus on, oh well, we can do parallel agents, and they do that to the extreme, and they're kind of in lockstep with how they're doing things. And yeah, there are some RL problems where that's actually not too bad. Like if you have a whole bunch of robots learning the same task, okay, maybe that's okay. But typically, for like if I'm thinking about myself, I cannot clone myself and have myself try out things I didn't do. You're starting to step into that world of leveraging the fact that you have a simulator rather than solving the kind of RL problem of deal with the consequences of your choices. And some people have started. I've seen some work that leans into that a bit more. I won't name specific things, but people will start exploring the fact like, oh, I can just restart the simulator from any point I want. It's like, if you're doing things like that, maybe you should just be using a planning algorithm and say you're doing solving a planning problem. That's fine. It's totally fine to solve a planning problem, but it's not RL. So I do worry that some of the results keep skewing towards exploiting the fact that there's simulators and just running absurd amount of compute. That's like hundreds of years worth of experience, which is like, yeah, it's actually kind of cool to see the limits that these algorithms will scale to that. But at the same time, have we really solved it? I don't know. It feels like not. And I say that with one caveat, which is it is worth mentioning that humans get a ton of data. The data in my life is very large, but typically these systems are very narrow in that task they solve. Like I have all this huge experience, but it also allows me to solve a whole bunch of things. And these RL agents, what they learn doesn't let them do that. So something's missing. And I do worry that the community has kind of gotten hyper-focused on just running simulators a lot and getting these big flashy results without pushing some of the core issues as much as we should.
We have a follow-up question there. Are there uses of RL that you thought were unique and unexpected in the sense that they didn't rely on all of the simulation-based training?
I mean, so to some extent, almost anything in robotics typically hits that. So I guess Jan Peters has a bunch of work that I always found pretty impressive of doing RL, usually bootstrapped from some kind of base level control things. But I think that's okay because the base level control things couldn't do, but then their RL systems would do. So like, it's like playing table tennis or something, like an arm that learns to do that with reinforcement learning. Like that feels pretty legit and pretty real to me, and it's a really hard problem. Basically, robotics is just hard from the start. I don't know how many of your students have tried to play with robots. Almost, in my experience, at least almost everyone has the same pattern, which is like, oh yeah, okay, I'll go do this, and I'll just do this one thing, a simple thing of making the robot do this, and then you realize just getting to that simple thing is horribly complex and difficult, and you can't even get to the RL part that you were hoping to get to before you can get over that. So getting robots to do anything is generally impressive. And so then if you show you actually have RL working on robots, I think that's a big deal. So almost anything in that space is just cool to see it working. As far as so I don't know if I'd say this is necessarily not simulators, because certainly you can use them. But other things that I think are interesting that I participated in a bit when I was at Brown, but it was still kind of an interesting way to look at things is like dialogue systems. Like there's a bunch of work that you can like solve dialogue systems using reinforcement learning like approaches. And it ends up being like a partially observable reinforcement learning problem where it's like, maybe there's some information the robot needs and it needs to talk to you to figure it out. And so it has these actions of asking you things to reveal the information that can make it work. And so you can frame it as this kind of interesting POMDP type problem, and you can run learning on it or do planning in it based on the information you're getting live from the person. And that can actually produce some decent results. So I think that's kind of an interesting thing because, I don't know, at least to me, thinking about dialogue as a decision-making problem isn't how like I would naturally intuitively do it, but it kind of makes sense and it works out. So I think that's kind of an interesting path. Generally, though, like decision-making is such a broad possible thing. Usually I'm of the mind of like, oh, it's easy to see how I can apply reinforcement learning to this because I can cast almost anything as a decision-making problem. Of course, then we get back to what I said earlier, which is you'd always use as much information, solve the most specific version of your problem. Like I can solve supervised learning classification problems with RL. I shouldn't do that though. It's probably a bad idea. I should use more specific algorithms for that. But yeah, so yeah, robotics type stuff I think is really interesting because it usually forces you to do real things. You can't cheat as much. And I think dialogue systems are kind of an interesting, wouldn't have expected that to be a thing for reinforcement learning type approaches.
I just kind of wanted to quickly chip in on the dialogue system stuff. I used to work on Siri at Apple for quite a while, and so I think about dialogue systems a lot. But it'll be risky though, because you can't predict what a person will say to a phone. Sometimes like we try to disambiguate what the user's intent is through questions, but they will just like totally start cursing at Siri or like throw the phone somewhere, and you'll hear like a loud sound. That might be some challenges, but it's certainly interesting. I think applying RL to dialogue systems.
Yeah, I totally believe that. I've done a fair bit of work, not so much a little bit in dialogue systems, but not so much, with just people being involved in the loop with reinforcement learning or planning agents. And yeah, people will always surprise you. They'll always do weird things, like either because they're malicious, maybe if they're insulting it, I guess, but also they'll just do weird things. It's like, that seems like totally not something you should do with the robot, but okay, that's what's happening, and you have to think about what that means for how your algorithms need to behave to compensate for it.
So quick follow-up. You mentioned, I guess you didn't say this, but well, okay, here's the question. So how much of the recent success you think is, new sort of innovation, right, versus just more compute? Just throw more compute to this problem, because, at the end of the day, OpenAI 5 is just using PPO. Right, of course. I'm sure that they tune and tweak and did things. But, also, a lot of the, StarCraft is not necessarily core reinforcement learning, but the training methodology, right? Like, how do you train? Is it better to do a league or, this kind of self-play, or what do they call it? Fake self-play? I forget the first word they use for
fictitious self-plays.
Right, fictitious. There you go. That's yeah. So how much do you think is kind of just like advancements outside of reinforcement learning versus core reinforcement learning techniques that are new and unique and that are actually making the difference?
Yeah, it's a good question. I feel like we are in a bit of a closer to application of ideas mode right now, which is probably fine, because you build up a bunch of ideas and then you see how far they go, and then you realize you've hit a wall, and then you build up some more ideas and you go. So maybe that's fine, but it does feel like we're kind of in that mode. Even the DQM paper, which I think is worth highlighting as a landmark paper, it certainly changed a lot about the field. So major credit for doing what they did. But when you look at the algorithm, it's a variant of fitted Q iteration. Like, the key idea was from fitted Q iteration, and that was it. And then there's some natural things you do to fix some of the problems. And so, super important paper to show. These tweaks make things really important, but a lot of the kind of core theoretical stuff is kind of earlier work. I think PPO it was also I think it's a very good algorithm that added a nice tweak to things. I think, is it the same author who did TRPO, which I think had a bit more of the theory that was kind of important for setting that stuff in motion. So I think that was
Schulman.
So, yeah. Okay. So I think TRPO kind of was a good piece of theory that led to then PPO, which seemed to be the one that took off. So I think was actually just a matter of compute. Like, TRPO was just a bit too compute demanding. Like, you have to compute second derivatives, and that gets messy, especially if you have like recurrent neural nets and things like that. You don't really want to be computing second derivatives. And then PPO is like, it's just a regular first order loss function. Great. So I think there's been some theoretical advancement, but a lot of it is just kind of let's find the kind of tricks that we need to make this existing theory work well, and move on from there. So the thing that I also kind of alluded to earlier that kind of has been bothering me more and more lately is just that, like, function approximation and dynamic programming doesn't really work, right? We have no real guarantees. Like, why should this work? Like, I know SGD, that works. Like, that goes to a local optima, great. Regular dynamic programming, that works, great. It converges. Put the two together, does it work? Well, no, but sometimes you can kind of make it so. So I think I've been working on this problem a bit. I don't know if I'm going to be the one to solve it. Maybe I'll come up with something. But that's just very frustrating to me. It's like, I feel like if we get to the point where we can say, yes, these safely work, and then you get into the mode of all we need to do then if it doesn't work well, it's like we just make the network bigger and we throw more data at it. That's a little bit better of a regime, more like the supervised learning regime, where you can just kind of make things bigger and it'll necessarily work. Whereas RL, although we have a bunch of these compute things, although certain flavor, I'll comment on that in a minute, but it's a lot of art still to make them work well, and I want to get rid of the art. We shouldn't have any art to make this stuff work. It should just work. So that's something. I think if we can get that solved, that would be a major advance for the community going forward. But I guess gets to my point, like these things that scale up big, they're typically pretty close to on-policy systems that use empirical returns. You look at the paper that just came out from OpenAI on the tool uses, the multi-agent, hide and seek stuff. Those on-policy, and it had an omniscient value function, right, involved. And so all this kind of trends and stuff, typically what it implies to me at least is like, we really can't do policy evaluation very well. Like it's just like, we'll just run it a bunch of times to get a bunch of empirical returns and we'll lean on that to a large extent. That's unfortunate. Like, shouldn't we be able to do better? Shouldn't we be able to get dynamic programming to like work well with this stuff? Hope so. Hope we can do that.
So by dynamic programming, you're referring to what is the deadly triad, the bootstrapping, function approximation, and off-policy learning? Okay.
Right,
just
right.
for the students to kind of...
That's totally fair. Right, yeah, so dynamic programming is like your original kind of base of how things work, and Q-learning and things like Q-learning are kind of like the model-free version of that, where it's like, we'll just kind of do samples instead of doing integrating over the transition dynamic probability distribution. But you think about it, it's like that part's not the hard part. Even if you have the model, you're just doing planning, function approximation, dynamic programming, these two don't mix well together. It's like, that's bad.
Exciting, yeah.
A quick follow-up. Can I? So
yeah,
you talk about we do a lot of things in the simulator because we need a lot of samples. What do you think are the ideas to take us the sample complexity lower so that we can come up with the simulator?
Yeah, so I do think some of that is solving this dynamic programming and function approximation issue, because then you can just get a set of data and crank on it, and if you get somewhere good, that gives you a lot more leeway. Right now, you can't, in these on-policy things, you have to get tons of samples because every time you change the policy, the value function is the actual value function is different, and you have to reevaluate it. So if you get back into dynamic programming land, you don't have to do that as much. Certainly you need to make sure you're still covering your space of possible things, but you can change the policy and dynamic programming will just keep working for you. So that's one thing that is, I think, important. The other is I do think we need more model-based RL. If we can get model-based RL to work, it is like kind of the greatest place to be, because I can change the task on you after you've learned for one task, and you're still basically good to go, right? Like you can just like, oh, okay, well, let me think about that for a bit, and I'll give you a new solution. I don't even need necessarily to get new experiences because I've already figured out how the world effectively works well enough to do planning and make decisions. So I think model-based RL, or things at least in that class of model-based RL where you're learning how the world works and using that to your advantage, are useful. So like some some things that I think are interesting are like the imagination augmented kind of learning, where they learned a model of the environment, and then the policy, the actor model, will like run simulations of what's going to happen, and it uses those as like features to the rest of the policy learning system. I think things like that are kind of interesting. I also really liked the value iteration networks paper along these lines. I don't know if people are familiar with that, but this is a paper where the key idea was like, what if we can like make the policy do value iteration in itself effectively? It's like built into the structure of the policy, but it's just a policy, and you go from there. I think that's really neat. Partially because I was having a lot of similar ideas, like kind of building off of the stuff I did earlier in Receding Horizon inverse reinforcement learning, where the idea was like, oh, you can think of this planning tree as just a policy, and you can like differentiate through it and learn things through that. But it wasn't in the RL scheme, it was for inverse reinforcement learning. But I was thinking we could probably do something like this there. And then the value iteration network paper came out and did a good job of finding out how to do that kind of stuff. So I think trying to bring models of the world somehow back into the RL paradigm is, learned models of the world. Otherwise, it's not RL. But like learning models and using those to your advantage, I think is going to be super important in the future. It seems to me like it's got to be the future. Otherwise you just can't solve new problems quickly on your own. As people, you can give me a new problem and I can think about it for a bit and like start off okay. If you're just doing pure model free, that doesn't really fly. You're going to have a hard time. So yeah, I think model-based reinforcement learning, or things like model-based reinforcement learning, end up being really important in that space.
Nice, thank you.
So we are, let's see, 50 minutes approximately from the hour. And I think we've gone over what, Chris? 5 questions?
Yep.
Too many follow-ups. And I asked a follow-up to a follow-up. So let's try to score a couple of questions there to see if we can, get more information in the remaining 15 minutes.
Okay. So let me jump around here. What's a sensible 5-year goal I can set for myself if this course is my first exposure to RL?
Yeah, I mean, so 5 years is about the length of time, maybe a little shorter, that you need for a PhD. So I think you can kind of set similar goals as you would for a PhD, which basically comes down to have one good idea, right, and make it work. And so the way I think to go about doing that is first find a problem that seems interesting to you. Take the approaches we have in reinforcement learning to try and solve it. If they solve it, then, and it doesn't seem like you have a lot of headway to do anything, maybe it's not a super interesting problem to continue working on. But if it doesn't work, right, now you're kind of in business, and you should figure out why it doesn't work. I think that should be your first step before you try and solve the thing. Figure out why things don't work to begin with. And if you get a real intuition about why it's not working, real understanding of why it's not working, and that seems like it's something that is somewhat general, then if you go and solve that kind of generalized version of the problem, it solves the problem you're on. That is a good place to be, kind of as a goal for end of 5 years, is that kind of space. You found a problem that things didn't work well, and you figured out why, and you found a solution to solve it.
This next question's an interesting one, and I'm not sure, maybe you hinted at this earlier. How can we ensure that policies learned with deep RL are safe and do not cause unintended and potentially dangerous behaviors?
Yeah, super hard. I don't think I will have the answer to this. I can maybe give some of my thoughts on it. So one way you can go about doing it is you can just constrain the policy to some extent, right? So this is something I think is really nice about actor-critic type algorithms. Again, I think actor-critic algorithms are cool for a lot of reasons, all fundamentally centering on the fact that policies as like a data structure are super useful in a lot of different ways. And so one of them is you can like constrain them, and you can make them like not do things. You can't do that in the value function because there is a value function that is true for what's going on. You can't just be like, yeah, but be more constrained. It's like, no, I can't be. I'm the value function. But the policies you can totally do. So you can totally constrain policies. So you can structure them if you have some knowledge about things that are unsafe to prevent them from just doing things that are unsafe. And then you have a proof that they're safe, right? It's like, oh, well, it can't do that. That's a pretty good answer for ruling that out. And some things you can do, and that's like, it's hard for me to describe quite how to do this, but like oftentimes you can structure your policies in interesting ways with some knowledge. So if you think about things like PID controllers, which are common in robotics, they're based on these control theory laws where it's like, oh, well, there's this target state variable I want to keep things at, and so what the algorithm does is it kind of measures your error from that, and it tells you how to adjust your control based on it. I don't want to get too detailed in it, but you can look up PIDs if you want. But you can kind of structure your policies around acting like PIDs, and then you get PID-like properties in terms of how they behave, and you can get interesting results from that. So those are some things you can do. Let's see. You can also add, if you don't want to explicitly structure your policy, you can also add like just kind of loss terms to it. So you can say, yeah, you're trying to maximize the value function, sure, but I'm going to impose some constraint on you about like you have to be close to some other ground truth policy that I have in mind for doing things. That's another path. And then the other path is you also just integrate other feedback from humans. So this isn't going to give you a proof of reliability because now you're asking to do learning, but you can let people give feedback and adjust your policies based on that feedback as they go. So maybe it starts to do something unsafe, but you can start correcting it, telling it it's doing a bad job at doing something. It can just be like, okay, I won't do that anymore, and it tries to generalize from there. So that's another way you can try and do it. But I think I think if you want to use some kind of powerful reinforcement learning, to a certain extent, you're going to have to give up proofs that it will always be safe unless you know a lot about the problem to enumerate those spaces. If you can't do that, then it seems like you're probably going to have to give it up if you want a system to learn how to do it. Please give it up strongly, I should say.
So this next question is on adversarial attacks. So you see these a lot in supervised learning. What are some of the exploits an adversary can launch in RL? Are there any ways to prevent these attacks?
So I guess it depends. So are we thinking about adversaries as a tool for researchers or as like people being malicious, trying to do things?
I think malicious.
Huh. Yeah. So there has been some work on, I think they call it like robust, like RL or robust MDPs or something like that, where you do pass the problem as you have an adversary who's choosing like transition dynamics or something that are the worst case scenario. Usually you're in the planning kind of space if you want to do this kind of thing, but there might be RL approaches that work in it. This might be a useful way because the outcome of that is saying like, if I have an adversary who's going to choose the worst possible world for you to be in, you have to, hedge against it, right? You have to do your best to prepare for that. So it becomes kind of like a min-maxy kind of way you're training your policy. So that's something you could do if you think you're going to have to deal with malicious agents going to mess things up or try and make it do the wrong thing. Otherwise, I think you might just run into the best you can do is make things as robust as possible to different kinds of states. So in supervised learning, that's a little easier to do. You can people do the things like, I'll take an image and I'll start tweaking it and see what happens if it changes. Can't quite do that in RL because there's no label, right? can't quite do that. But you can try and push things into different state spaces. So RL oftentimes is fairly sensitive to the state distribution it's seen. And so, in fact, the policy gradient theorem is kind of built that in as a feature, right? It's like, I want you to do well on the state distribution you're going to observe following your policy. So maybe you actually want to relax that a bit and be like, we're going to put some other states in there. We're going to make sure you can work well from a whole bunch of different things. I'm kind of reminded of a paper on Dagger, which was kind of a behavior cloning like paper where you're learning from people giving demonstrations. And what they the problem they were dealing with was, yeah, if you give demonstrations, it might look good on just your training data as if it was supervised learning. But when you run it in the environment, its little errors that it makes start adding up, and eventually it finds itself in like bizarre states it had no idea how to behave in, and things go bad. And so that paper was about, we can intermix people taking back control. So you let it run for a while and then take back control from these other places. So that was about how to make that more robust in general. But that might be a technique just for checking your general robustness, is start pushing your agent in ways that it wasn't intended to. It didn't intend to work. So you can maybe just make it throw in different actions every once in a while and see how well it does, or train it against those kinds of things, and see what happens from there. That might be one way to get around it. I'll have to think about what it would mean for a malicious person like attacking an RL agent to do weird things. I guess you can exploit weird state features if you understand it well enough. And that could be, I use that as a feature. So in work I did on the coach algorithm, which was learning from people, I found this as a feature of the way the learning worked, where you could like teach it to follow a ball to start. This is all just the same policy you're training, but you start by just kind of teaching like a robot to follow a ball that you can hold, and you can move around and starts following the ball. And then you could do cool things where you can use that ball to guide it through, an environment to do something else and give it positive feedback for that, and then you take the ball away and things work. So I saw that as a feature, but that's potentially also a way that people could maybe do bad things. They can find the features that are relevant and somehow like make them more present to cause it to behave in certain ways. I don't know. I'd have to think about it a bit more about how people might try and hack an AI, an RL policy. Interesting.
So this next question is a little more philosophical, and I think it relates to the robotics and dialogue systems you brought up. These systems have the potential to disrupt workforces. What is our obligation as practitioners?
Yeah. So this is a really important problem. There's a lot of issues in AI right now as things go, like biased data sets and things like that, causing all kinds of problems. So I think it's super important question. I don't think I have the answer, but to some extent, to the extent that you can be thinking about ways your system might be either misused or just might cause problems if it was deployed. So if you're like deploying a decision-making system that somehow has to deal with, it's making decisions about people's lives, that could be scary. You might want to be really careful about how you're training the system, what things it's latching onto, in the same way you have to be careful with supervised learning. So to the extent that you can just be mindful about how the thing you're building is going to be used, you should be. I do think beyond that, it is worth saying that while we bear some of this responsibility in thinking about it, we're also probably not the people who should be solving it. I'm trained in how to write these algorithms. Public policy and law and all that is a very complex world that you don't want me trying to solve it in the full way. I will do a bad job.
You want to bootstrap it?
Yeah, right. Yeah, it's like, well, we'll just get another agent and we'll start training the agent. I'm sure this will work out well.
We just need to create an optimal decision maker.
Yeah, we'll just make an optimal decision maker, right? Just that we'll solve that small little problem, and we're good. Yeah. So you probably don't want me trying to solve the big problem. I do think what that means is we like need a new class of people thinking about the social implications. People working in public policy, people working in law. Actually, we had an employee. I don't maybe I shouldn't name her. I feel like it'd be good to name her, but maybe it wouldn't. But she used to work at Cogitai, and now she's going off and doing like stuff in AI and law, which is like super fascinating, area to like merge those two things. But I also think it's really critical as we get further along these lines, as AI becomes more and more part of our society. We're going to need people who kind of understand AI and understand law and know how to structure things, think about these things. So I think we need more people who are doing things like that. I think if anyone in your class is kind of straddling, like they're taking this class to learn about RL, but they also have interest in some other kind of public policy or law or things like that, I totally support that. I think that's a great idea. We definitely need it.
One more question?
Sure.
Go ahead, Chris.
Okay.
One more.
All right. So there are many resources for learning about deep RL. So there's papers, blog posts, implementations, YouTube lectures. What recommendations can you give a person coming into this field for making the most of their time? How do you manage the overload of information when trying to advance your knowledge?
Yeah, it is a lot. And I almost worry that we're going to run to a problem of just good work gets lost in the noise, which is an issue. Like you look at the number of papers NeurIPS or AAAI are getting these days, and it's growing like exponentially. So there's a problem there, and so there's a community issue on that, on making sure the good ideas populate to the top. But from a personal position of just trying to learn things, I wouldn't worry too much about that fact. You don't actually need to know the vast majority of papers that are published. And really, when it comes down to it, the fundamentals are what I think you should focus on. It kind of took a while for me to get a feeling that's like an intuition about reinforcement learning, like how MDPs work, how value functions behave. Like it seems like it's straightforward when you look at it, but there's all kinds of really fascinating dynamics about what goes on in these systems, and it just takes a while before it starts becoming intuitive about how all these things tend to operate. So getting that level of understanding is just kind of focusing on the fundamentals, really understanding what's going on with these things. And then once you get there, once you understand the fundamentals, once you understand what the problems are in the field, like why can't we do this thing well? What's the limitation? What's the challenge there? When you start understanding that, reading papers in the area becomes really easy. You basically just look for the part of what is the actual problem that they're trying to address. If you're reading a paper and they're describing the problem they're going to set out to solve, and you don't really understand exactly what the problem is or like why it's an issue, or maybe you just don't even know what like some of the terms are, like just stop reading the paper there. Like you're not going to get anything of value from that point. If you're interested in it though, go figure out what that problem is, go learn about that. And that can sometimes take a lot of time to go back in time through different literature and find the right things, but you can start asking the right questions about why you're confused about what the problem is. And then once you do start understanding these problems and you go into a paper, you say, oh yeah, okay, that problem, got it. And then you'll look at their solution and you can be like, oh yeah, okay, that makes sense. Like if you understand the problem, the solution is usually pretty easy to follow. And then it's just a matter of what you get from the papers. Like that's an interesting way to approach it. I hadn't thought of that. Or you see, wow, maybe I considered that, but I didn't realize it would be as effective as it is, and things like that. And so then you can kind of pick and choose which papers are useful, and you can get through them a lot quicker than when you start. But I do think if you are hitting the point where you don't really understand the problem they're describing, you should probably just stop there and try and figure it out. I don't think you'll get a lot more from that. So I would not get discouraged with the sheer quantity of it. The main thing you want to learn is just the fundamentals, so you really understand all the issues at play. And then the papers are just like making your life easier at that point, because, oh yeah, I want to know about this, and you find a paper that's like, oh yeah, they were also thinking about that, and here's a solution then.
Excellent. And then with that, well, on behalf of the students, the teaching staff, all the TAs over here, and Professor Isbell, thank you for spending a whole hour of your time with us. I feel that it's very valuable that we can bring people with the knowledge and the expertise to our course. And yeah, I thank you for lending that time, right, to just
absolutely
give it out. And then so to the students, if you have feedback and you don't mind, sending your name as well, if you mind, just make sure that you do an anonymous follow-up and leave your comments to James, and I will forward all of those comments to him in a couple of days, so that in a way of clapping at the end of the session. We're online, so there's no clapping, but thank you so much for spending the time with us, James. I appreciate it.
Yeah, thanks for having me.
Thanks, James.
All right.
And with that, I'm going to stop the recording. Bye.